dynamics. Fancy word for motion. It sounds impressive, doesn't it? And of course we have good old Newton to thank for all this and his wonderful laws of motion, which I'm sure you've heard of, but maybe not actually heard of the actual laws of motion. And there is law 1. Corpus omni preserveri in statu suo quiescendi vel movendi uniformita nisi quatinus a veribus impressus cogitor statum illum maturi. Come on, does anyone here do Latin? She said, none of you know if I'm right or wrong anyway. It doesn't matter. Fortunately, I can translate. Oh, there we go. So, everybody continues in a state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. So what that basically means is this. If I'm here standing still, I'm going to stay standing still. Unless some force is impressed upon me. So whether that be someone come along and push me in the back, or push me forward, or I choose to move a leg forward, or something like that. Right? But similarly, if I'm moving, I will just keep moving until some force comes along. That force could be someone grabs me and stops me, or it could be I reach this brick wall right over here. Okay? So that would be, and that's really all the first law is saying. Okay. Second law, probably the most famous of them all. But again, you may not have seen it in this form. Mutationium motus proportionalium. It's basically this one. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which the force is impressed. You may have heard of it another way again. So it's saying the motive force is proportional to the change in motion. Well, force is proportional, change in motion, change in velocity, acceleration. Force is proportional to acceleration. Well, if it's directly proportional, it's equal to some constant, and as we now know, that constant turns out to be the mass. Force equals mass times acceleration. That's all the second one's saying. The third one, the one people often get wrong, actione contrarium. Yeah, the actione contrarium? Actione contrarium. Contrary. Yeah. Opposite. See? Here we go. Most people, it's most often misquoted as to every reaction there's an equal and opposite reaction. You might have heard it said that way. But what it actually is this. To every action there is always opposed an equal reaction, or the mutual action of two bodies upon each other are always equal and directed in contrary parts. Okay? We will come to what this really means later as we go along. But basically it's saying forces are always in balance. Right? Now, you know there is a force acting on me. Even though I'm standing here right now, there is a force acting on me. What is that force? Gravity. Well, that's the acceleration. Oh. It would actually be the force due to gravity. Okay? Weight. Weight is that force. So weight is the force due to gravity, mg. Okay? But yet, I'm not going down like this. Oh my gosh, gravity. Oh, help me. All right? I'm not. Why? Because there is also a force being opposed to me at the moment. A reaction force. Anyway, well, that's, I guess, the simplest way I can explain that. Let's have a little bit of talk about acceleration. We have seen it is, in fact, the second derivative of displacement with respect to time. It's also the derivative of velocity with respect to time. So that's fantastic. When we've got acceleration as a function of time, we can play with that. We have now seen d dx of half v squared, another way of writing acceleration, and that's great when it was a function of displacement. V to v dx, although I do use it for when it's a function of x as well, but this one really comes in handy because you could also write acceleration as a function of velocity. And that's when v to v dx comes into its own, is when we have it in that sort of form. Okay, a very, very old question. Assume that the Earth is a sphere of radius capital R, and that at a point little r, which is bigger than capital R, from the centre of the Earth, the acceleration due to gravity is proportionate to 1 on r squared, little r squared for that matter, and is directed towards the Earth's centre. A body is projected vertically upwards from the surface of the Earth with initial speed, capital V. I guess the reason they're just using letters is it generalises the problem, because we can solve it then for any situation. Once we come up with an answer, we just sub in for those variables. We are going to prove that our projectile, good old Bob, is going to escape the Earth if and only if that velocity is greater than or equal to the square root of 2gr, where g is the magnitude of the acceleration due to gravity at the Earth's surface. Right, going to draw a little picture there. The big blue circle, that's the Earth. O is the centre of the Earth. I'm going to project vertically upwards along the red line. So there's Bob, somewhere on its path. Now, some conditions. I know at the Earth's surface, little r is equal to capital R. So basically in this problem, instead of using x for displacement, we're using little r. Okay. V, so little v, the velocity is capital V. And the acceleration, which I'm calling r with 2 dots, is minus g. They told me it was g, but it's directed towards the centre. Okay. I also know that when it stops eventually, velocity will equal 0. So that's another thing I know about this problem. Okay, there's Bob. Now what we do in extension 2 is we draw ourselves a little force diagram and we say, all right, what are all the forces acting on this particle? What are all the forces acting on this particle? Can you tell me any force that's acting on the particle? The weight force. Okay. So the way I set the problem up, the resultant force. Now let me talk about the resultant force. The resultant force is not an actual force. It is the result of all the other forces. Okay? That's what we try to find. I've drawn that in blue. In red, this is the force that's actually acting, which is the force due to gravity. But in this case, if you look at what they said, the force due to gravity was proportional to 1 on r squared. So it's not as simple as just saying mg in this case. It's some constant. That constant I've called mu, because it's fun to say. Mu. And when you put mass in front of it, it looks like mu anyway. How cool is that? So the acceleration is mu on r squared, but we want forces, so it's mass times acceleration. So m mu on r squared. There are no other forces that we've been told about. So the resultant force, mr double dot, will equal all of the forces. So it will equal m mu on r squared, but you'll notice I put a negative because it's in the opposite direction to my resultant force. So I make it negative. Well, the masses cancel and I get an acceleration in terms of displacement. Remember, we're using little r to represent displacement. Okay. Now, I can work out what mu is because we were given some conditions. Here they are over here next to my lovely picture of the Earth. When little r equals capital R, the acceleration is minus g. So let's sub that in and we get that mu is g capital R squared. Okay. So I now have a new improved formula for acceleration. Minus g capital R squared on little r squared. Okay. V to v, well, dx, but in this case dr, because we're using r to represent displacement. So v divided r is minus gr squared on r squared. Now, why did I use that? Because I want to come up with a link between velocity and displacement. So it makes sense that I would use the dvdr one, because that relates velocity and displacement together. Okay, separate the variables. I have the integral of v to v is equal to, and I'll take the constant out, the constant minus g capital R squared, dr on r squared. Now, they told me when displacement was capital R, the velocity was capital V. I'm trying to find a link between velocity and displacement. Multiply both sides by 2, because I know this is actually half v squared, but I'll multiply the other side by 2. So on the other side I get 2gr squared. Okay, let's sub in. And make v squared the subject. There's a formula for little v squared. Little v squared. Now, this particle has to escape the Earth. If it escapes the Earth, that means it doesn't stop. Because if it stops, what's going to happen? It's going to fall because gravity is going to pull it back down. So it never stops. So in other words, the displacement has to approach infinity. Because if it approaches any other point, then it's going to stop. And then it's going to come back. So I know if it never stops that little r approaches infinity. So what is the limit of the velocity as r approaches infinity? Well, let's have a look. Little r is only in one place there. That's on the bottom of the fraction. And if infinity, I sub that into the bottom of the fraction, we get 0. So I'm just left with capital V squared minus 2gr. But I know little v squared has to be positive. So capital V squared minus 2gr must be greater than or equal to 0, which means capital V squared is greater than or equal to 2gr. So therefore, in order to escape, v has to be greater than or equal to the square root of 2gr. Now, in this case, I didn't have to worry about the negative velocity, because yes, v would be plus or minus, but it has to be the positive case, because if it was the negative case, what am I doing? That's what we're going to drill down into the centre of the Earth. So logically, it has to be the positive case in this one. Okay. All right. Now they're saying, well, let's assume v is in fact that escape velocity, the square root of 2gr. Now it wants us to find the time it takes to get to a height of capital R. All right, there's our formula for little v squared. But we've now said v is the square root of 2gr, so something really nice happens. If v is the square root of 2gr, then v squared is 2gr, 2gr minus 2gr, 0. So my formula is just v squared on 2g capital R squared. We want to link displacement and time. Well, velocity would do that, dx to t. Well, I've got velocity squared, so I know velocity, remember, it's going to be positive because it's not coming back. Right? We've determined this is the escape velocity, not coming back, so it can't be negative. So I know velocity is the positive square root, which means dx to t, or in this case dr to t, is the square root of 2gr squared on r. Let's find that relationship between displacement and time. Turn it upside down. Separate the variables. Okay. When time was equal to 0, displacement was capital R. We wanted to go to a height r above the surface. So in other words, displacement from the centre of the Earth is 2 capital R. And obviously we want to find the time of that. This is a little problem we have to solve. Okay. Well, little t, square root of r is actually r to the power of half. Add 1 to the power over the power, we get r to the power of 3 on 2, but times 2/3. Substitute in. Remember, r to the power of 3 on 2, if I put it in third form, is r root r. So when I'm substituting 2r, I get 2r root 2r minus, substitute in r root r. Okay. That is the answer. It's just not what they asked for. We're now going to play with our algebra and get there. Okay. I've factorised out the r root r, you'll notice. So r root r, if I factorise that out, leaves me with 2 root 2 minus 1. So that's in the parentheses. Now, out the front, what have I done here? Oh, square root of r squared is, of course, capital R. That capital R will cancel with that capital R. So I now have the square root of r on 3 root g. 4 minus root 2. Well, I've multiplied the root 2 inside the parentheses. And now, I think that's what they wanted, was it? Except it was all one square root, or... So, well, I'll just put the third sign all around the r on g, and I've got what they wanted. So, yes, mere mortals would look at the question and start shuddering and go, oh my gosh, that's just a little bit of algebra, which us super mathematicians can do. And as promised, I'm only giving you 3 questions to look at. Oh, no, look, come on. You should know me better than that. No, if I promised 3 questions. 3 questions.